Okay, so calculate the thermal energy that leaves the gas. Technically, they're asking for the Q for this process, for process BC, right? But let's just think about this, right? Remember that Q is equal to the change in internal energy plus the work, right? Well, there's no work done here because the change in volume is 0, right? And work is pressure change in volume, right? So there's no work being done here, right? What's going on is that the gas is cooling down and that's dropping the pressure, right? So the heat that flows out of the gas is the same as the change in internal energy, okay? Basically, this is what you have, right? Right, these guys are the same, okay? Q and change in internal energy. So how do you find the change in internal energy? In subtopic B2, in the data packet on page 13, right, you have a formula that says that U, the internal energy, is 3/2 nRT, right? So you could do this. The change in U is equal to 3/2 nR change in temperature. We could do this because we know that this temperature here is 679.549, and we know that this temperature down here, since it's the same temperature as A, right? This is an isothermal process, right? This temperature here is 169.887, right? So you could find the change in temperature and do this, right? Okay. But you can also do this. It's also, since nRT equals PV, right, we can also find the change in U. Change in U is also equal to 3/2 change in pressure times volume, okay? Try doing it both ways. Convince yourself that these are the same thing, okay? Now, the 5400 looks awfully familiar, and there's a reason for that. So when we get to the last question, when we look at the efficiency, and we'll look at all of the processes, right? But indeed, yeah, there's a reason why we've arrived at that number before. Okay. Anyway,